we want to analyze and graph the function y equals f of x equals x plus 5 over the quantity x plus 7 squared. So first thing we want to do is identify what kind of function we have. We notice that the numerator is a polynomial of degree 1. Okay, the power of x is 1. Okay, the denominator is a polynomial of degree 2. If you expand this, you get x squared plus 14x plus 49, which should be pretty much immediately obvious. Okay, so and that implies this is a rational function. Okay, if you have a rational function, the first thing you always want to do is determine when the numerator is 0 and when the denominator is 0. So rational function you want to find when the numerator is 0, and you want to find when the denominator is 0. Those are the first two things you want to do. You also want to look at end behavior and possible asymptotes. You're going to have a vertical asymptote when the denominator is 0, if the denominators can be 0. But we could also have oblique asymptotes and horizontal asymptotes. So we have possible asymptotes, could be oblique, horizontal, or vertical. First thing we want to do is find when the numerator is 0 and when the denominator is 0. And also, we're going to want to find the Y-intercept. That's pretty much automatic with any function. So I didn't think to write that down, but find your Y-intercept, or intercepts if it's not a function. It could be a relation where you'd have more than one Y-intercept. Okay, so what do we get? The numerator is 0. Well, the numerator is x plus 5. That occurs when x is negative 5. Now, if the numerator is 0 and the denominator isn't, that's going to mean that the rational function has to be 0 when x equals negative 5. That gives us a point on the x-axis when we want to graph it. Excuse me. Denominator equals 0. X plus 7 squared equals 0 occurs when x plus 7 equals 0. I just take the square root of this and the square root of this. Be plus or minus, but plus or minus 0 is 0. And so that occurs when x equals negative 7. So we have the beginnings of what we need to construct the graph. So we might as well go ahead and start that. Let's also find the Y-intercept. F of 0 equals 0 plus 5 over 0 plus 7 squared, which is 5 over 49. Approximately 1/10. 5 over 50 would be 1/10. Well, let's go ahead and sketch a set of coordinate axes and see what comes out of this. Okay, so we know that the numerator is 0 when x equals negative 5. That implies the point negative 5, 0 on the graph. So we go over here. Let's put unit markers here. And let's go over to negative 5. And we have a point on the graph at x equals negative 5. Now we do have to make sure that negative 5 is not also a 0 of the denominator. If it is, then the function is going to simplify. but clearly the denominator is not 0 when x equals -5. In fact, it's -5 plus 7 is 2. Square that, you get 4. So the denominator is 4. So when x equals 0, or when the numerator equals 0, the value of the function is 0 over 4, which is, of course, 0. The denominator is 0 when x equals -7. So we go over here even a little further. And we're going to sketch the line x equals -7. Now we should understand that when x is close to -7, the function has a value. Well, the numerator is going to be close to -2, and the denominator is going to be close to 0. Now, the numerator isn't going to vary much from -2 if we move just a little ways to the right or left of x equals -7. But the denominator is going to approach 0 as we approach this line from either side, meaning that the denominator is going to go into the numerator an increasing number of times. Since there's no limit to how small the denominator can get as you approach this x equals -7, there's no limit to how large the result can be. Okay, so we're going to have then a vertical asymptote at x equals -7. Also, so we get a vertical asymptote at x equals -7. Near x equals -7, numerator is near -2. So that if we divide the numerator by this denominator that approaches 0 as we approach x equals -7, we're going to get a negative result. Okay. The other thing is, well, we're going to get a negative result if this is positive. Well, for any value of x except -7, x plus 7, the denominator is positive, so denominator near 0 implies f of x is equal to or approximately equal to -2 over a positive number near 0. Okay? The closer the denominator gets to 0, the bigger the result will be, but the result is negative. So this f of x will be -2 over a positive number near 0 equals a large negative number. Okay, that means that as we approach x equals -7 from either side, we're going to get a large negative number, and at least on this side, we expect that large negative number to come up and somehow go through x equals -5, and then to approach the Y-intercept. I'm looking for the Y-intercept, 5 over 49. Okay, that's about 1/10. That's going to be about here. So we kind of expect the graph to come up, maybe come up over this, and then come down here. And we'll see what else might happen to it. On this side of the graph, well, we really need to start looking at the end behavior of this function. So you should think about what the end behavior ought to be. hopefully you've paused and given that some thought. I'm kind of almost out of blackboard space. I'm going to say it, and then I'll probably write it a little bit more on another board. But as x gets big, the denominator is the square of a big number. The numerator is only equal to that big number. So if x was 1,000, well, 1,007 isn't much different than 1,000. When you square it, you get something close to 1,000,000. X plus 5, if x was 1,000, you'd have 1,005. So you'd have 1,005 over something close to 1,000,000. So it's like 1,000 over 1,000,000, which is 1/1,000th. Okay, so the denominator for large values of x is going to get a whole lot bigger than the numerator. Now the other thing is, when x is less than -5, on this side of -5, the numerator is negative. To the right of x equals 5, the numerator is positive. The denominator is always positive for any value for which the function is defined. It's not defined for x equals -7. So the numerator has to be positive, and it has to approach 0. The denominator to the left of x equals -7. The numerator is, well, that's to the left of x equals -5. The numerator is going to be negative. The denominator is positive. So any place over here, the function has to be negative, but the result has to approach 0 as x gets large. So we have a graph that kind of looks like this. Now, the approach to the -1 is going to be pretty smooth. It's not going to have a dent in it. And the way I've drawn it, it kind of does. So it probably doesn't come this high up above the x-axis. Probably stays pretty close to the x-axis here. And that's consistent with the fact that you're squaring the denominator. And as you move away from the x equals -7 line, you get some pretty big denominators. Now I've written in a comment here that kind of summarizes what I just said. For the end behavior means if you have x of a large magnitude, the absolute value of x is large. If the absolute value of x is large, it's so big that the 5 and the 7 don't really make much difference. You essentially have x over x squared. So you have essentially 1 over x. And in that case, you have a large numerator, x. If x is larger, the magnitude of your numerator is large. But your denominator, being the square of a large number, is very, very much larger, which means that f of x is going to be near 0. And it's going to be more and more so, more and more near 0 as the magnitude of x gets larger. And that's consistent with what this graph does. It comes down here and approaches a horizontal asymptote with the x-axis as x gets very large. And on the negative side, it approaches an asymptote with a negative x-axis. It has to approach from below here because to the left of -5, the numerator is negative, denominator is positive. To the right of x equals -5, numerator and denominator are both positive. Okay, so we found with the numerator 0, with the denominator 0, we've applied what we found there. We've looked at the end behavior, and we've found horizontal and vertical asymptotes, horizontal asymptotes from the end behavior, the vertical asymptote from the 0 of the denominator. We didn't consider oblique asymptotes, and I'll just say that that's not going to be relevant here. That's going to occur only if the degree of the numerator minus the degree of the denominator is 1. That is, if the degree of the numerator is 1 greater than the degree of the denominator. In this case, the degree of the denominator is 1 greater than the degree of the numerator, so we will not have oblique asymptotes. We've also found the Y-intercept, so we've checked out these important highlights. Now we'll look at this in the next clip for a different kind of a rational function.